In the name of Almighty God, our Master Sankar, today I want to talk about multibody dynamics module in quantum multiphysics simulation software, the theory of the multibody dynamics interface, the multibody dynamics theory chapter outlines the theory for the multibody dynamics interface. The joint theory section describes the types of joints and the additional functionality available. The cam follower theory section describes the theory for the cam follower connection. The gear theory and the gear pair theory sections describe the theory of all the gear types and gear pairs types, respectively. In the end, the rigid body contact theory section describes the theory of modeling rigid body contact and friction between standard shape rigid bodies. Now I want to go through the multi-body dynamics interface. The multibody dynamics chapter describes all the physics nodes available in the multibody dynamics interface: joints, spring dampers, cam followers, attachments, and rigid domain-based motions, initial values, gears, gear pairs, chain drives, and rigid body contacts are described in detail. The rest of the physics nodes are described in the structural mechanics module user's guide. Now I want to go through the lumped mechanical system. The lumped mechanical system chapter describes all the physics nodes available in the lumped mechanical system interface. The corresponding theory for all the physics nodes is described in the theory for the lumped mechanical system interface section. Now I want to go to the second chapter, multibody dynamics modeling. This chapter introduces you to the theory for the multibody dynamic interface features. In this chapter, we want to go to the multibody dynamic model, joints, attachment, cam follower, springs and dampers, gears, gear geometries, chain drive, chain geometries, bearings, initialization and time-dependent studies, geometric nonlinearity, multiphysics couplings, the multibody dynamics model. Rigid and flexible parts are one of the big advantages of the multibody dynamics module is the ease by which you can mix rigid and flexible parts. Usually all or the majority of the parts in a multibody simulation are rigid and are thus represented by only the degrees of freedom of a rigid body. The material model for a rigid parts is rigid material. Sometimes, however, you may want to include the flexibility of one or several domains. To do that, use the linear elastic material. This is the default material model in the multibody dynamics interface, so the workflow is to add as many rigid material nodes as needed and assign domains to them. The remaining domains will then be linear elastic and thus flexible. By adding a solid mechanics interface, you can get access to many other materials models for the flexible domains. Linear flexible components can be reduced to computationally efficient low order models using the component model synthesis or CMS technique. Such reduced models are defined by adding a reduced flexibility components node and can be used in dynamic as well as stationary analysis. Now I want to go through the meshing. A rigid domain is only represented by a set of ODEs representing the equations of motion for a rigid body. The mesh on a rigid domain is only used for integrating properties like mass, center of gravity, and moments of inertia. This means that the mesh can be much coarser than what is usually the case in a finite element model. Since there is still a computational and memory consumption cost involved with each element, you should strive for a very coarse mesh in rigid domains. When meshing a flexible body, you have to make the same considerations as when meshing any other finite element method. In the multi-body dynamics interface, the default shape function order for the flexible part is linear, as opposed to the solid mechanics interface where it is quadratic. The purpose is to keep down the number of degrees of freedom. In those cases, where the stiffness is more important than stress evaluation. If you need more accurate stress result, you can either use a finer mesh or change the discretization or to quadratic serendipity or quadratic in the discretization section settings of the interface. Connecting parts section. The most important feature for connecting parts is a joint. A joint will in general allow relative movement between two parts in one or more degrees of freedom. This is described in detail in the joint section. It is also possible to connect parts by springs and dampers as described in the springs and dampers section. A part can be connected to several joints, springs, or dampers. The way to attach them differs between a rigid and a flexible object. A flexible body must be connected through an attachment as described in the attachment section. Add an attachment node to the model and select the attached boundaries. The attachment is then referenced in, for example, a joint. A rigid domain can be connected directly, but just specifying the location of the connection point doesn't even have to physically inside the rigid domain, since the domain can be considered as an abstract object. A rigid domain can also be connected by an attachment. This is convenient if you consider switching between a rigid and a flexible formulation for this domain. A rigid domain can consist of a selection of several geometrical domains. These domains will act as a single rigid object irrespective of whether they are geometrically connected or not. Adjacent domain selection selected in different rigid material nodes are independent objects and can even penetrate each other. Now I want to go through the gears section. Gear is defined as a rigid body. A finite stiffness for the gear mesh or gear tooth can be specified in the gear pair node while connecting to other gears. Similar to the rigid domain, the gear is a material model which is mutually exclusive to all other material models. The only material property needed is the mass density. Now I want to go to the connecting to other physics interface. When modeling flexible parts, it is possible to add other structural mechanics interfaces to get additional functionality. If you have the structural mechanics module, the solid mechanics interface has several features which are not available directly from the multibody dynamics interface. If you have the nonlinear structural materials module or the geomechanics module, then you can get access to the whole range of material model by adding a solid mechanics interface. In this way, you can, for example, include a hyperelastic or elastoplastic domain in your multibody dynamic simulation. If you have the structural mechanics module, you can add a shell or beam interface to model thin or slender flexible objects. There are two ways in which you can connect to objects from the other structural mechanics interfaces. You can connect through joints or springs. In the solid mechanics shell or beam interfaces, you can add attachment nodes. Such attachment will then appear in the list of attachments in various features in the multibody dynamic interface. You can also connect to objects in the shell and beam interfaces through the solid shell connection and solid beam connection multiphysics coupling. Using the looped mechanics system interface, you can model circuit representation of mechanical systems of masses, springs, and dampers. With the lumped structure connection multiphysics coupling, you can connect the lumped mechanical system interface to the multibody dynamic interface. Now I want to go through another chapter, joints, about joints. A joint is used to allow a certain type of relative motion between the two components it connects. A joint is a global feature that needs two attachments, one from each component. One attachment acts as a source and other as a destination. The two attachments belonging to a joint can be attachment features, rigid material features, or combination of the two. The source attachment can also be said to be either fixed or to have a given base motion. In the case of a fixed attachment, it cannot translate or rotate. This avoids the modeling of extra fixed rigid domains when a structure is grounded. The, the base motion is generalization of the fixed attachment where the environment to which it is attached can have a prescribed displacement, velocity, or acceleration. The source attachment moves independently in space, whereas the destination attachment is constrained to follow the source attachment, allowing for some relative degrees of freedom in the form of translation or rotation. The relative degrees of freedom are determined by the type of joint. In each joint, the relative degrees of freedom are represented by ODE variables. The degree of freedom that are constrained in a joint can be rigidly constrained or contain some relative elastic displacement. The rest of this section has these topics. The first, joint types and degrees of freedom, selecting attachments, joint axes and local coordinate system, positioning the joint center constraints, locking springs and dampers on joints. Elasticity in joints, prescribed motion, applied forces and moments on joints, frictions, computing joint forces and moments, initial values of joints, degrees of freedom, creating joints automatically. Joint types and degrees of freedom. Table 2-1 lists the joint type for three-dimensional models based on the possible relative degrees of freedom. Table 2-1 joint types and degrees of freedom in three-dimensional size. You see, we have a prismatic joint, the total degree of freedom 1, the translation degrees of freedom 1, rotational degrees of freedom 0. Hinge joint, total degrees of freedom is 1, translation degrees of freedom 0, rotational degrees of freedom is 1. Cylindrical joint, the total degrees of freedom is 2, translation degrees of freedom is 1, rotational degrees of freedom is 1. Screw joint, total degrees of freedom is 1 star, translation degrees of freedom is 1, rotational degrees of freedom is 1. Planar joint, total degrees of freedom is 3, translational degrees of freedom is 2, and rotational degrees of freedom is 1. Ball joint, the total degrees of freedom is 3, translation degrees of freedom is 0, and rotational degrees of freedom is 3. Slot joint, total degrees of freedom is 4, translation degrees of freedom is 1, and rotation degrees of freedom is 3. Radius slot joint, total degrees of freedom is 2, translation degrees of freedom is 1, and rotation degrees of freedom is 1. Clearance joint, total degrees of freedom is 3, translation degrees of freedom is 0, star, and this star means that we have a footnote for them. Rotational degrees of freedom is 3. Fixed joint, total degrees of freedom is 0, translation degrees of freedom 0, rotation degrees of freedom is 0, and it does make sense because it's a fixed joint. The stance joint, total degrees of freedom is 5, translation degrees of freedom is 2, rotation degrees of freedom is 3. Now, the next table, the continuing, the universal joint, the total degrees of freedom is 2, translation degrees of freedom is 0, rotation degrees of freedom is 2. So for a screw joint, the 2 degrees of freedom are linearly dependent. For clearance joint, all three translation degrees of freedom are not completely restrained, but allow with a limiting value, and triple star for distance joint. All three translation degrees of freedom are not independent. And the next table, table 2-2, lists the available joint features for two-dimensional models. Table 2-2, joint types and degrees of freedom in two-dimensional. Joint type prismatic joints, the total degrees of freedom is 1, translation degrees of freedom 1, rotation degrees of freedom 0. Hinge joint, rotational degrees of freedom is 1, translation degrees of freedom is 0, and rotation degrees of freedom is 1. Reduced slot joint, total degrees of freedom is 2, translation degrees of freedom is 1, and rotational degrees of freedom is 1. Clearance joint, total degrees of freedom is 1, translation degrees of freedom is 0, total rotational degrees of freedom is 1. Fixed joint, total degrees of freedom is 0, translation degrees of freedom is 0, rotational degrees of freedom is 0. Distance joint, total degrees of freedom is 2, translational degrees of freedom is 1, rotational degrees of freedom is 1. For clearance joint, both translation degrees of freedom are not completely restrained but allow with a limiting value. For a distance joint, both translational degrees for freedom are not independent. Now I want to go through the selecting attachments. There are no rules for how to select the source or destination attachment for joint, but one selection can be more convenient than the other. The only difference is that the interpretation of certain quantities changes if the source and destination are swapped. Some of the important quantities and the relationship with the source and destination attachments are: the joint coordinate system follows the source attachment. All the relative degrees of freedom are created on the destination attachment. The joint movements are computed around the center of joint attachment to the source attachment. In the ball joint and slide joint, the inclination angle is the angle between the reference axis and the destination axis. The axial rotation occurs about the destination axis. This reference axis is defined on the source attachment. In the planar joint, all axes in each subnode follow the source attachment. Positioning the joint center. You can position the center of a joint in different ways: at the centroid of the source attachment, at the centroid of the destination attachment, at the centroid of some selected entities such as boundaries, edges, or points. As a special case, in a single point can be used explicitly given coordinates in a Cartesian axis. Attachments must be used for flexible components and are optional for rigid components. The first two options are only available if an attachment is selected as source or destination. So thank you so much for watching my tutorial video until the end. Today is 3rd day of June 2026. Time is 7:48 p.m. And also you can download the simulation file from github.com/mahsascript.